Okay. Good morning everyone, welcome to the next lecture of energy conservation and waste heat recovery. In the last few lectures you have learnt about heat exchangers, the fundamentals of heat exchangers, the different kinds of heat exchangers as well as heat exchanger networks. So today what we are going to talk about is a special heat exchange device. It is also called heat exchanger in the sense that it helps in exchanging heat from a hot stream to a cold stream or a hot surface to a cold stream, but it does so in a sort of unique manner. The name of that special heat transfer device or heat exchange device is heat pipe. Let me write it down. So now what is a heat pipe? If I tell you in a very crude sense, a heat pipe is actually a cylindrical device, or it can be a flattened cylindrical device also, or flattened circular cross section I mean, which is an extremely good conductor of heat. Okay. It has a very extremely high thermal conductivity or effective thermal conductivity along its axial direction. So let us say if I draw something that looks like a pipe in this manner and call this a heat pipe, then the effective conductivity along the axial direction, K effective let us say in the axial direction, is very high. Now what do I mean by very high? It is of the order of 1000 to 10,000 watts per meter Kelvin, depending on a variety of parameters which we are going to discuss later. Now is this number high? Let us see, to compare copper, which is one of the best thermal conductors that we know of, the thermal conductivity of copper is around 400 watts per meter Kelvin. Thermal conductivity of aluminum, which is also a very good conductor, is around, the pure aluminum is around 238 watts per meter Kelvin. Okay. So what does it mean? What does it mean for us, or how can we make use of this very high thermal conductivity? So think about it. If this is my heat pipe and on one end I expose it to a heated ambient, okay. So I will say hot ambient. On the other end I am using a blue color here, and this is, I would say, a colder ambience, a colder ambient. Okay. And what I want to do is transfer some of the heat which is at this location, the hot ambient as we are calling it, and we want to transfer some of the thermal energy that is present over here to the other end, okay, where it is cold and we want to heat it up, or we want to utilize the thermal energy at this point. Okay. So effectively from our basic knowledge of heat transfer, we would say that we need a good conductor of heat. Now how good is good? You would say we can use copper, we can use aluminum, but what I am saying is let us use a heat pipe, okay, because here the thermal conductivity in this axial direction is very high. So therefore we can have a very efficient conduction of thermal energy from the hot side to the cold side with minimal thermal resistance, or in other words minimal temperature drop. Okay. So this in essence is what a heat pipe is in layman's term. The next question is, what is it that gives this heat exchange device such a high thermal conductivity? Because normally, unless it is a very specialized and expensive material, we do not know, even if we talk about diamond and all, we cannot get this kind of thermal conductivity values. Okay. Maybe 1000 with diamond is possible, but not definitely an order of magnitude higher. So the question therefore is, what is it that makes heat pipes such an efficient conductor, such an efficient rather thermal conductor. Okay. So, that is the question that we are going to answer next. So, what I will do now is I will quickly switch over to the slide that I have playing here. It is an animation, and using this animation, let us talk about what is happening inside a heat pipe. So, as you can see from outside, the heat pipe will appear to be, in this case it is showing to be a cylinder with a circular cross section. As I said, it does not necessarily have to be circular cross section, but whatever it is. So, on one end of the heat pipe, as you can see, we have this heat in. So, this is that hot ambient that I was talking about. Okay. So, essentially one end is heated, the other end is exposed to a colder ambient, or other end is kind of cooled. So, what does a heat pipe contain? First and foremost, it is not a solid rod or a pipe, rather it is a hollow tube, okay, sealed on both sides. So, it is a sealed hollow tube. Then what happens is, in the annulus, so around the inner diameter, we have a special material which we call a wick. Typically the wick can be a fibrous material, it can be a sintered material, it can be in the form of grooves. We are going to talk about that, but essentially this wick, the function of the wick, or there is a special function of the wick that we are going to see next. Okay. Now, coming back to the construction again, the third thing that is there inside a heat pipe is a few drops of liquid. Let's assume it to be water for now, because that is the one that is most commonly used. It is a few drops of water inside at a subambient pressure, at a very low pressure. So, the whole heat pipe, again to repeat, it is a hollow pipe made of, let us say, a material like copper. Then inside, on the inner diameter around the annulus, you have a wick material, and then you have a few drops of liquid, say water, inside at a subambient pressure. So, the whole heat pipe is kind of evacuated to a low pressure and then sealed, so that finally what you see from outside is a sealed device with all these components inside. Now, what happens when we heat one end? The few drops of liquid that is present vaporizes. Remember, we have evacuated it, so its boiling point, let us think, if we consider water, the boiling point of water, if we goes down if we reduce the pressure. So, for example, if we evacuate it to, let us say, 0.3 atmospheres, the boiling point will be around 70 degrees centigrade. And similarly, for other lower pressures, we can get the boiling point of the saturation temperature from steam tables, we know that. So, this few drops of water then vaporizes, and as it vaporizes, it starts flowing, the vapor starts flowing through the core, which is hollow. So, it starts to flow from one end to the other end. As it reaches the other end, which is cooled or subjected to a colder ambient, the vaporized water or the water vapor condenses. Okay. It gives up, the rejects heat and condenses again back to liquid water, and the liquid water then comes back to the hot end through the wick because of capillary action. Okay. Again I repeat, on one end we are supplying heat so that the few drops of liquid vaporizes, the vapor then flows along the hollow core to the other end where it is cooled, and therefore it condenses and converts back to liquid, and the liquid is driven back again to the heated end through the wick due to capillary action. Think of it, when you light a lamp, let us say during Diwali, we light a lamp and then we have this wick and we heat one end. If we light the fire at the end of the wick, and then what happens? The oil that is in that lamp, in the diya, actually goes from one end of that wick to the other end, which is lighted because of the capillary action. Okay. So, it is the same thing, and that is why this we also call this material as the wick, because it is doing the same function. All right. So, a few terminologies to end this slide with, the end at which we are supplying heat is known as the evaporator end or the evaporator section. Okay. Why evaporator section? Because the liquid is kind of getting converted to vapor, and that is why it is evaporating. Therefore, there is the evaporator section. Similarly, therefore, the other end where it is condensing back to liquid is known as the condenser section, and the section in between where the vapor is flowing along the core and where we normally see very low temperature drop is known as adiabatic section. In many cases, the adiabatic section is also insulated around, so that we minimize heat loss from the outer walls of the heat pipe. Okay. So, this in a sense is the construction of a heat pipe and the way it functions. That is what I am trying to show through this animation. Okay. And I also want to acknowledge my previous employer, Intel Corporation, from where I have got this animation. Okay. All right. So, let us come back, and now that we understand how a heat pipe functions, let us see therefore look at the construction inside once more, try to draw it again, and this time not just as a black box or a just like a pipe from outside, but let us also draw the internals here. Okay. So, this is how it looks from the outside, but on the inner side what we have, I am exaggerating it a little bit. This is my wick material, okay, which I am drawing with the green ink. On one end, I am supplying heat, and let us normally, using the normal nomenclature, we will use the symbol Q, and on the other end I am extracting that heat out. Okay. So, here the heat is rejected by some means, because this end is kept at a lower temperature, and therefore, what is happening is the water vapor or the water is converting to vapor over here, and then flowing through this core, and similarly from the other end also it will do the same. We are assuming an axisymmetric geometry here. So, this is how the vapor is travelling, and then on the other end where it condenses, it comes back through the wick due to capillary action. Okay. So, is it clear now? So, as we said, this end we call it the evaporator section. Many a times we will just denote it as E, and this end we will call it as a condenser section, and many times we will denote it as C. The middle portion over here is the adiabatic section. Okay. So, keep in mind, adiabatic section, it means that there is minimal heat loss. It may or may not be insulated. The way I have drawn is it is insulated, just to show that it is an adiabatic section, but many a times even if you do not insulate it, which is actually true in many applications, we normally do not have too much of heat loss from one end to the other. Okay. It is just because the vapor flows at a very high speed. All right. Okay. So, therefore, now let us look at a few applications, or okay, let us look at this slide again. This is kind of a more detailed rendition of what I just drew in this schematic. Again, heat in from one end, evaporator section, heat out from the other end, condenser section, and then this is the wick through which the liquid flows back. This insulating portion, as we called it, is the adiabatic section, which, as I want to repeat, may or may not be insulated in the practical application. Okay. So, let us think about it, and we will come to this slide again. What exactly is happening? Let us focus on the paper here. See, we would have studied through our heat transfer what is a liquid pumped loop. Let us say I want to have liquid cooling. I have a heat source over here which I need to cool, and I have liquid flowing through it. Okay. So, cold liquid comes in. Okay. So, let us call it, first give it a heading, liquid pumped loop. So, you have liquid in, cold liquid that comes in, and hot liquid that goes out. This is TH, let us say, this is TC, this we know. Okay. Then what happens? The hot liquid, because this is liquid, we cannot just reject it to the ambient. So, then what happens? We let this one go through a loop, and we bring it to another section where we have another heat exchanger, where this hot liquid or fluid has to reject the heat. Okay. So, over here there was heat addition, and over here there is heat rejection. Okay. The hot liquid again cools down and comes out as cold liquid, but then you have to pump it, you have to send it back, because this is a closed loop. So, therefore, what we needed was, we needed a pump to pump the cold liquid back to the heater source, or the heat source that we want to cool, or the source of heat from where we want to remove thermal energy. So, this is a typical liquid pump loop. Okay. Compare it with what is happening in a heat pipe. Do we have a hot section through which, from where a cold liquid is removing heat? Yes, we do, which is the evaporator section. Do we have another section where the hot fluid, which can be single phase or two phase, is cooled down to its original temperature? Yes, we do, that is the condenser section. Do we have a pump? Well, we do not have a pump, but the function of that pump is being done by the wick material through its capillary action. Clear? So, therefore, what I am trying to say is, over here heat pipe is very similar to a liquid, let me say two phase pumped loop. However, the pumping action is performed by the wick. Clear? Okay. So, this is what I am showing here from Professor Amir Faghri, who is a well known authority on heat pipes, and this is in his book. He has shown this figure trying to show the functioning of a heat pipe on a typical TS diagram. This TS diagram, like a simple Rankine cycle, is very familiar to us. So, he has modified a Rankine cycle. So, 1 to 2 is what is happening in the evaporator section. You have start with liquid, and what you end up at the end of the evaporator section is actually vapor, which can be saturated, it can be superheated also. Okay, that is what he is saying, saturated or superheated. 2 to 3 is the condenser, because this is where the vapor pressure drives through the adiabatic section to condenser, and from 3 to 4 the vapor condenses releasing heat to the heat sink, or this is where the condenser section is, the vapor condenses back, and finally here the pumping action of the capillary brings it back from 4 to 1. This is slightly different from what we normally see in a pump, where we typically see an isentropic line going higher up and the temperature also going up. In a wick, that does not happen, the temperature does not go up, nor is it isentropic, but this is what is happening. But in many, in a sense, this is very similar to a pumped loop or a Rankine cycle, which we just discussed. Okay. So next, what we will do is, this is a very, as I said, this is a very high thermal conductivity, extremely high effective thermal conductivity. I have a small video which is available in the YouTube, and you will see, you will find this link also here. I will just play it. It is a simple experiment to show how effective or how efficient this heat pipe is in terms of its axial thermal conductivity. Okay.
Hello, and thank you for joining Advanced Cooling Technologies for this lesson on heat pipe basics. A heat pipe is sealed under vacuum with a small prescribed amount of working fluid. During non-operation, the fluid is contained inside the wick structure that lines the inner diameter of the heat pipe. When a heat source, such as an electronic component, generates heat, the fluid vaporizes at what is known as the evaporator section. The fluid vapor quickly spreads to the other end of the heat pipe using pressure generated by the temperature difference. At the opposite end, known as the condenser, the fluid gives up its latent heat, which is rejected to an external heat sink. The fluid then returns to liquid form, and the wick structure passively pumps the fluid back to the evaporator using capillary force. By utilizing liquid and vapor phases, the heat transport is extremely efficient. Because it's a closed-loop system, heat pipes operate continuously and passively, creating a very reliable component in your thermal management system. Now we'll go through a quick demonstration on heat pipe thermal conductivity. In this demo, we'll examine the heat transfer capability of a copper rod versus a heat pipe. On the outside of both samples, there's a paint that changes from green to yellow when the temperature exceeds 40 degrees C. We'll now place the copper rod into the hot side of the unit and let it heat up. The hot side is well above the 40 degrees C color change temperature. Copper has a thermal conductivity of 400 watts per meter K, which is high for most metals. You can begin to see color changing as the copper conducts heat away from the heaters below. Now we'll place the heat pipe into the hot side. Notice that the heat pipe reaches steady state almost instantaneously with minimum temperature gradient compared to the copper rod. Now we'll move both the copper rod and heat pipe into the cooler side. The heat pipe simply changes the direction of the thermodynamic loop and reaches the lower temperature steady state in seconds, while the copper rod struggles to reach that steady state temperature. ACT would like to thank you for joining us. Hopefully everyone learned a little bit about the advantages of heat pipes. For further...
Okay. So I think in that video what we saw was there was a copper pipe, there was a heat pipe, and there was some temperature sensitive dye on the surface, and you could see that when both the rods or both the pipes, solid copper and heat pipe, was dipped in the warm section, the heat pipe heated up much faster compared to copper, and similarly when they were again put back in the cold section, the heat pipe again cooled down much faster. Okay, and this goes on to show that its effective conductivity is much higher compared to that of copper. Okay. The other advantages of heat pipe, as you can see, as it's light, it's reliable, it's cheap, and more importantly it's passive. We were comparing it with a pumped loop, and as you can see here we don't have a pump. The wick performs that function, so there are no mechanical moving parts, so it's very reliable. Once it is made and it is sealed, it performs very reliably and goes on functioning for many years. Okay, but again keep in mind, this is not a heat removal device. Okay, it's a means of transporting device. It's a heat exchange device, right? It's not a thermal solution. It's a means of transporting heat from point A to a point B with minimum thermal resistance, which is what we are trying to do in terms of waste heat recovery. If we think about it, we have what do we have? We have thermal energy due to some source which otherwise would have been wasted, and we want to extract whatever is possible from that source of thermal energy and utilize it somewhere else where it can be put to benefit to our benefit. And so heat pipe will enable us to do that very effectively. So, let me just, okay, this is what we saw. Let us look at one of these applications, which is called gas to gas heat recovery. Okay. And this is where the schematic is shown. Let us think about it as two chambers. On one hand you have hot waste gas which is coming, and on the other section of this which may or may not be directly connected, it can be a remote, it can be remotely located also, you have cool air and which we want to heat up, and that heated air can be used either for room heating or for any other process. And again, to make it more generalized, it does not have to be air, it can be any other fluid as also. Okay. So, we have hot waste gas coming in over here and cold air which we want to cool, which we want to heat up, sorry. So, the way it is done is, you have an array of heat pipes like this, all these circular pipes that you see inside, these are heat pipes, very high effective thermal conductivity in the axial direction. So, on one end, if you just connect the two sections by an array of heat pipes like this, what happens is the thermal energy or heat will be conducted very effectively with minimal temperature drop from the hot waste gas, or rather hot gas which would otherwise have been wasted, to the fluid which we want, in this case air, which we are trying to heat up. Okay. So, this is this is one of the very common and well established applications of heat pipes in terms for heat recovery or waste heat recovery. Okay. It is used, just to let you know, the plate this that is there, that is separating the two sections, is many a times called the splitter plate, and the splitter plate, as we will see later, the splitter plate is also used, the orientation of the splitter plate can be changed, it can be kept perfectly vertical so that the heat pipes are horizontal, or it can be inclined to give some inclination to the heat pipes, and as we will see that the performance of a heat pipe is a strong function of its inclination as well as other geometric parameters. Okay. So, this is what we will start with in the next lecture, as well as we are going to talk about a few other applications of heat pipes in terms of waste heat recovery. Okay. So, again, thank you very much, and we will continue on this topic in the next lecture.